Hello, everybody, and welcome to some more of the RenderMan Art and Science Fair. So before we get started, we just want to remind everyone that you can mute actually up in the little corner, the little notifications. You see a little bell icon. You can hit that, and that'll kind of quiet those down. The other thing is if you have any questions for us, make sure you use the Questions tab. So welcome to the RenderMan 24 for Technical Directors. I am David Hackett. I am the Technical Writer at RenderMan, and I would like to welcome you to my beautiful view of Seattle. You will have to kind of take my word for it. So my job today is to introduce some of our lovely presenters and not screw anything up. Today we'll be hearing from Philippe, Per, Trina, and Tom. And so let's get started. We'll be hearing from Philippe first on some OpenColorIO.
So we're going to talk a bit quickly about two new features of RenderMan 24. First, we will have a quick once-over on OSL. So, of course, we've been using OSL since RenderMan 19. But this is the next step of the evolution of OSL in RenderMan. So C++ patterns are deprecated. That means that all patterns are now written in OSL. We improved our internal OSL support to make sure that we could translate our pattern library to OSL without any functionality loss. That includes a little detail like you have options to have exactly the same noise as the C++ noise that were in RenderMan if you want to have the backward compatibility, but it's a bit slower than the native OSL nodes. OSL noise, sorry. So basically, if you're using noise, Perlin, cell noise, all those things, we have a compatibility mode. That allowed us to implement exciting new nodes as well. That I already presented in the previous presentation. 24 is using the latest OSL 1.11. So that means that you have all the new fancy coding features like struts and overrides and operators and things like that. Of course, we still have the SIMD execution to have a faster execution on AVX type AVX and AVX 512. We are now compatible with MaterialX OSL library because of this new version of the OSL library. So that's important. It means that people can start playing with that if they want to. And of course, the main reason why we wanted to move to OSL was to transition to XPU, which means that all the patterns that are in RenderMan 24 will run on XPU as well. So as a last thing, of course, closure are still not supported, just because if we implemented them inside the renderer, that would basically mean that a lot of people would not use the more sophisticated way of creating materials that we want to push forward. So, and also it allows people to easily, the C++ API allows people to create new BXDFs if they want to. So that's something that's much more difficult because the closures are kind of frozen in time. Another really important thing is OpenColorIO. So finally, we tackled color management. So as you know, probably, OpenColorIO is an industry standard color management system, allowing a pipeline to produce consistent results. It has three goals: define the main color space in which all computations will happen, provide ways to convert from other color spaces to the main color space and back. This is important to make sure all inputs are in the same space and that output will be consistent. Finally, defines viewing functions to adapt to various displays and viewing conditions. This sounds complicated, and it is a bit, but artists only need to know a few things to get the most out of the system. So RenderMan 24 will ship pre-configured with ACES 1.2. We removed the camera profiles from the configurations because they were adding hundreds of megabytes to the downloadable package, but you can download them in the ACES repository should you need them. The renderer defaults to no color management for backward compatibility. And also because you need to understand what to do beforehand. In this example, I have a simple cornel box rendered without the color management. You can see that some areas are clumped or burnt out. Also note the washed out indirect illumination on the ceiling. And now this is the same render in ACES. The clumping is gone and the colors are more saturated everywhere. There are a few reasons for that. First, we rendered in a color space called ACCG, which allows for more saturated colors than your typical sRGB. Second, ACES applied a special function to adapt the image to the human visual system and avoid clipping intense pixel value. The result is a very natural looking image. So again, without, and again with, I hope this is visible on the video feed, but it makes a big difference. How does it work? In practice, you will have to tell the renderer which OpenColorIO configuration you are using. Once it knows, the rest should be pretty much automatic. If disabled, the renderer assumes sRGB Rec 709 like it does in 23. When you select ACES 1.2, you're using the factory configuration. Should you wish to extend or replace it, use the custom option. In that case, we support the usual options to specify your configuration. At render time, the renderer will use the linear role, or rather the rendering role. This is something that I changed recently, as defined in your OpenColorIO configuration file. The lights will adapt to emit in the correct color space automatically. If you set up your DCC app correctly, all flat colors will be passed in the correct color space, and you will just have to make sure your input texture are in ACCG. It is a lot more efficient to pre-convert your textures, but we also provide controls to apply the color conversion at render time. It is quite expensive, though. TXMake has been updated with 2 flags, or OCIO config points to your config file, as usual, and OCIO convert text source and destination color spaces. Of course, you can use roles instead of color space names if you want to. We also updated the texture manager, so it uses automatically the same OpenColorIO config as your DCC app and gives you options to color convert incoming textures. We also designed new rules to pick good defaults for various image types, and we support adding the name of the input color space in the file name, and that will be automatically used to choose the conversion parameter. Our image viewer got an upgrade too, so you can display roles instead of color space names to simplify the user experience. We also build hierarchical menus by family if you choose to display the color space names. And we added OpenColorIO looks support, and our factory config ships with a number of useful looks. Of course, we improved the preferences as well to handle all those new functionality. So that's it for me. Thank you very much. And I will introduce now Per Christensen, who is going to tell you a bit more about sampling improvements.
Hi, my name is Per Christensen. I'm going to talk about blue noise samples. Let me just bring up my slides here. Bear with me for a second. All right. Yes, my name is Per Christensen. I'm a principal software developer in the RenderMan team. I'm going to talk about blue noise samples. And so this was all inspired by a wonderful talk by Laurent Belcourt, Atlastic Graph. So the idea here is to optimize sample sequences such that neighbor pixels are as different as possible. I'll show some examples in just a moment. The biggest benefit is for low sample counts. So if you're doing interactive rendering, you're moving your camera around or changing your scene, you're spending a lot of your time actually watching renders at low sample counts, like 1 sample per pixel or just a few. And this is where this new feature really shines. So let's look at some examples. This is a very simple scene, just 2 spheres on a plane illuminated by a large area light source. Both images are rendered with just 1 sample per pixel. On the left, without blue noise. And as you can see, there tends to be clusters of dark pixels clustered together, and there are clusters of bright pixels as well. And it gives this look that can be called clumpy, is one word for it. On the right-hand side, the same scene rendered with blue noise, still just 1 sample per pixel. As you can see, it's much more visually pleasing because the bright pixels and the dark pixels have been interleaved in a much more pleasing way. And I should emphasize that the render time is completely the same. It's just that we're utilizing the sample tables in a better way. Here's the same scene rendered with 4 samples per pixel. Here, the difference between blue noise and not is not quite as clear, but it's definitely still there. And the advantages kind of taper off with higher sample counts. Here's another scene. This is subsurface scattering. We're now back at just 1 sample per pixel. The guy on the left is rendered without blue noise, and he kind of looks like he's made out of some kind of very coarse gravel, is how I would describe it. Whereas the guy on the right with blue noise, it looks maybe he's made out of some very fine-grained sand. Definitely, if you squint your eyes, the guy on the right looks closer to the final converged image. Yeah, here's another example. This is depth of field. So this is a teapot that's very much out of focus. So on the left, without blue noise, the pixels, the dark pixels tend to cluster together, and the bright pixels will cluster together. Whereas on the right teapot, rendered with blue noise, the dark and bright pixels have been interleaved in a more visually pleasing way. Motion blur, that's a 1D effect. So this is a sphere, a white sphere that's streaking across the screen. On the left, again, clusters of bright pixels and dark pixels, whereas on the right, it's more visually pleasing because those dark and bright pixels have been interleaved in a better way. Here's everyone's, this is our favorite vehicle. So this is the van that's illuminated by an environment light and a handful of other light sources. If you look at the inserts with the magnification, if you look, for example, at the turn signal, the orange turn signal, on the left, the white speckles are very noisy looking, whereas on the right, the white speckles are more evenly distributed. Another place where the difference is clear is the tire. So on the left, it looks very dirty, like it's just been out driving through some mud or something, whereas on the right, it looks more clean. And even though, in both cases, it's just rendered with a single sample per pixel. So the benefits of blue noise, I hope I've convinced you that it's more visually pleasing. There is another bonus, which is important. So using blue noise samples gives the denoiser better input to work with. So it's better able to distinguish between noise that it needs to eliminate and features that it needs to preserve. And I think also blue noise samples will improve adaptive sampling. This is something I haven't actually tested or measured, but it seems intuitively that it should. There's another interesting quirk about these blue noise samples. So in a mathematical sense, if you go and measure the average error in each pixel, it doesn't actually show an improvement in that way. So the math doesn't really capture the fact that the images look better. But at the end of the day, what we care about is visual quality, and as also this bonus of the denoiser being given better input. Let's see. So the biggest benefits, as I mentioned, are at low sample counts. That's why I showed images with 1 sample per pixel and 4 samples per pixels. But again, that's really what matters most if you're doing interactive rendering, because as you're changing your scene, you spend a lot of your time looking at samples or looking at images with those sample counts. Also, the biggest benefits are when a single sample domain is dominant. So, for example, an environment light or very strong motion blur or something like that. But in the end, the pixels converge to the same result as before without blue noise. They're never worse. So just a few details. So as I mentioned, this is inspired by a talk from Laurent Belcourt last year. There are a few differences though. So we use progressive multi-jitter samples instead of the Sobel sequence as the input to this optimization. And we also generate larger tiles. This means that we have fewer visible repeats of noise patterns across the image. We generate both 1D, 2D, and 3D samples in this way with the blue noise. And this new feature will be available in RenderMan 24, both in RIS and XPU. So that's all I have. I'm really super excited about this new feature. I think it's a nice visual improvement. So please enjoy. And with that, I'm going to hand the virtual microphone over to Trina and Tom, who are going to talk about statistics.
Thanks, Bear. I'll bring up my slides. All right. Hi, my name is Trina Roy. I am the stats project lead on the RenderMan team up in Seattle.
And I'm Tom Nettleship. I work in the Lightspeed team at Pixar in Emeryville. And for the last year, I've been working with the RenderMan team on upgrading their stats and diagnostics.
We're very happy to have him. And we are here to introduce the new stats and diagnostics system for RenderMan 24. So first of all, what do we mean by stats and diagnostics? In general, we mean the tools and information that give insight into what RenderMan is doing during the course of a render, whether it be a single render or multiple renders. And that could be performance bottlenecks, time and memory, or the effect different elements in the scene may have on time and memory. And this is all information that is telling a story. Every user, depending on what your role is or what your job is, has a different story that they want stats to tell. So for example, an artist may want to see a memory footprint or memory footprint change as their settings are changing. A developer may want to see the inner loop timings without having to stop the render, add print statements, rebuild, and rerun. A TD may want to dig into details like, why is the smoke on my teapot taking so long to render? And the producer wants the big picture summary for long-term planning. How much will this sequence cost? How much will the show cost? That type of thing. So you might be thinking RenderMan already has stats, right? Well, it does. It has had since the early days. And there is a powerful amount of information available there, but the ways in which a user can access that data are limited. And most importantly, that data is currently not available until the render completes. And in these days of always-on rendering, we want always-on stats as well. So what do? We start from scratch. So this system was built from the ground up, starting with a whole new way of thinking about stats. We can't know what a user wants to see, how they want to see it, or when. So we wanted to make sure that the data was not only comprehensive, but also always available and allow users to have control over how, when, and what they see. And we broke this philosophy down into 6 specific goals. First and foremost, stats should be live. That was our #1 goal. When a render is running, we wanted to be able to answer the question of what is happening right now. In addition, the user needed to be able to interact with the stat system, adjusting or toggling diagnostics during a render. Obviously, stats need to be accurate and fast, at least until you want to deep dive into a scene element, at which point you want to be able to take a performance hit in order to get that deep analysis and then go back to your standard run. We also wanted to make sure that we didn't put any limitations on how you view and analyze stats, so it was paramount that the presentation side of the system be extensible. And finally, with all of this, we needed to balance the amount of information available. So we wanted more than a high-level summary, but not Valgrind or Valtune. We wanted, or VTune, excuse me. I keep saying that. We wanted to find that sweet spot right in between. So arguably, the coolest part of the system is the fact that the stats are live and dynamic. At any point in a render, you can tap in and see what is happening. For example, with a heads-up display in a DCC or with a web page displaying charts and graphs coming from the live stream. And this is true of both farm renders and live renders, or IPR, depending on what DCC you happen to be using. So you can connect to a running farm render to debug something that might be going wrong during a 12-hour render, or you can watch your stats change live as you're making edits during lookup. And interactive doesn't just mean you can see the stats as the render progresses. It also means that you can change how the system or the metrics are configured without restarting your render. A default set of metrics will always be gathered with minimal performance impact, but the dynamic aspect of the system means that you can dial it up or dial down the granularity according to the task at hand. So what allows us to do this is the decoupling of the presentation data from the instrumentation, presentation of the data from the instrumentation that's in the rendering code. So instead of waiting for the render to complete and write out the data, we created an extensible plugin system for extracting and analyzing the data. A pipeline can have any number of these presentation plugins, which we refer to as listeners. And each listener plugin controls how much and how often data is received. For example, a live HUD may update a ray count or the ray count every second, and another listener may be reading the same ray count metric, but only updating it every 30 seconds to update a database. RenderMan 24 will ship with built-in listeners, including JSON file output, live data presentation, and there will also be API and example code for building your own custom listeners. So how does this compare to stats, the current system of stats? This is how the current system works. Stats are initialized at render startup, data is gathered during the render, and then at the end of the render, once the render is finished, the data is collated and written out to an XML file. With the new stats, the difference is that data is collated continuously and available to listeners at any time. You can still get that comprehensive report at the end of the render, but you can also get a snapshot of that report anytime during render. But you can also see live updates in the DCC HUD, a web client, stream it to a database, whatever your listener plugin configuration is. But enough talk. Let's see how this actually works in practice. And for that, we're going to hop it over to Tom.
Thanks, Trina. So in my day job as a Lightspeed TD at Emeryville, I'm involved in a lot of optimization work and finding out why things are slow or too much memory or noisy or a bit unstable. And I often find myself wondering, what is that farm job doing? And I currently can't find out. I can wait till the end of the render. I can look at the XML. I can try and work out why it took a long time to render. But what I really want to do is be able to look at it right now and see why it's so slow or where it's spending its time. So here's a demo of our work in progress. Sorry, let me just click some buttons. Our work in progress web client, which shows you how we can do that with a new stat system. So I've just kicked a farm job off, and I have a web page on the left. And this is a recording. Very shortly, you will see me go to our stats client. I'm going to type in the URL of my farm machine. Now, in a real installation, my farm navigation software will provide me a handy way to click on a task and go to this interface. But for the purposes of demos, I've typed in the URL of the farm machine. I've connected the stats interface, and now I see a bunch of high-level stats. So I can see some gauge of the progress it's making, some high-level stuff about memory and time. I can see the process memory updating in real time, and I can see a sort of a high-level breakdown of the categories of work the render is currently doing. So we can see this render is doing some texture sampling and some shading, a little bit of lighting, and a little bit of ray tracing. At the bottom there, you can see there's a graph showing the rays it's currently tracing, and we've just passed one iteration, so that was our time to first bucket phase over, and we're now into ray tracing proper. You can see that pink ray tracing wedge start to go up. So that's the sort of the live activity that job is going on with at the moment. And on the left, you can see the process memory sort of tailed off the way RIS renders do once they've built the scene. This render is using our WebSocket interface. I'll just pause it for a second because I'm going to start another one up shortly. On the right-hand side, we'll start up a gRPC-based client. Again, a different listener, and it's going to listen for a different bunch of stats from the WebSocket one. This one's a debug listener, so it doesn't look fancy. It's a wall of text. Let me unpause, and we should see that start up shortly. The point is that you can have multiple listeners. Each of them is pulling out only the stats that you need to present to the users, and therefore the render is only paying the overhead of the stats that all of the listeners actually pull on, and at the rate they pull on. So while these live ones are attached to the farm job, there's also another one which is going to save out an equivalent to the XML later on. And that's pulling data at a much lower rate, and then it'll write the file out with the checkbook. So here's the gRPC listener that's just started up. And you can see, I think that's all of our ray trace stats, and just in a completely undigestible form. But basically, these are using two completely separate interfaces. So once we disconnect these, there is no more overhead. And that's the really key thing. One of the problems that we would have with stats gathering and trying to find out where a render is going wrong is maybe it goes wrong one time in 10. And so you see it go wrong, and then you try and instrument the executable or turn on some more debug options, run it again, and it doesn't happen. With this approach, you can see the one that's going wrong, you can attach to it, you can try and diagnose why it's going wrong, and you can do something about it. And you can only achieve that if the capability to do this is always available in all of your farm renders. And to do that, we had to implement a system with a very, very low overhead, so that when none of this cool stuff is going on, you're not knocking down your overall farm performance. So I'm going to unpause now, and we'll switch to a different demo. Here we go. So this is a demo of an interactive render session. So this is my local machine now, not a farm machine, still using that same web client. Once released, we will have equivalent functionality to this web client integrated into all of the DCC, so Katana, Houdini, Maya, and I guess Blender. But for now, for testing, we're using the early work in progress web client for the same thing. So I just kicked a preview render off, and now I'm going to connect my web client to it, and we'll see the stats thing light up and the similar stuff starts happening. But now it's watching my local live render go. Sorry, preview render. And in the case of this one, we can see that it's doing a little bit of shading, a lot of lighting, a lot of ray tracing. There's no texture work done. There wasn't really any rib parsing. And that's because, you know, this is a version of Barley without any shaders on at all. And so you can see this render started very quickly. The iteration count's going up very fast. We can see the memory footprint on the left. I'm now going to swap over to another session where on the same machine, I have a Katana where Barley is going to be rendered with textures. We'll see a different result and a different bunch of stats. So again, I've clicked a preview render off. I connect this client to the second Katana session. Initially, we don't see much. The memory is going up on the left, and we can see a bit of stuff about CPU time. Now we start to get some texture sampling and some shading going on. This is building the scene, and now this is a textured and shaded version of Barley. This is probably doing work to displace the meshes when it's tessellating them. But there's no real ray tracing yet. We can see the way the memory is going up. And in a short while, we're going to see some rays start to get traced. There we go. So some rays start to get traced. We'll see buckets fairly soon. There we go. So that was our time to first bucket phase done. And now we start to see the pink wedge of the ray tracing increase in value. And there's our first iteration done. This one iterates much more slowly than the other one. Yeah, so that's it's pretty cool that you can see it working interactively like this. And in a live render, you could make changes to your shading or your lights or whatever and see the way the stats reacted. So if I just pause here. So we've got 5.6 gig of memory used, and then we've got 3.7. And you can see the way the pie charts on the unshaded one are different from the pie charts on the shaded one. And so we're able to look in detail at the different ways that the renderer is doing its work. Why so long to first bucket? That is a question that I ask myself every day, Chris Rutledge. And these new stats are one of the things I'm hoping will help me answer that question. So this is an early work in progress client. At release, you'll be able to do more than see the high level stats it's giving you. We want to be able to drill down into things like this shading, where to find out where that 50% is going, and drill down further and find out like which shader is the one that's spending most of my shading time. And then I can try and make a decision about, is it reasonable that the shader for Barley's ankle is super expensive? And maybe it isn't, and we can have a conversation about how to optimize that. Okay, so that's a quick demo of our early prototype of the ways that you'll be able to have new workflows using the stats system. Now I'll pass you back to Trina.
Thanks, Tom. Now that you have gotten a taste of what the new system looks like, it looks like there's a lot of excitement for it over on the chat channel, which is great to see. Here is what will be in the box for RenderMan 24. As I mentioned before, we will provide built-in listeners for live stats display and file output, and there will also be example code for listener plugins. In addition, there will be APIs included for both listener presentation and for instrumentation if you want to instrument your smoke procedural or whatever you want to do. It is worth noting for the 24.0 release cycle that the legacy XML stats will remain unchanged and the current stats will continue to be maintained. After the 24.0 release, we will continue to expand the instrumentation in both XPU and RIS. And it's worth pointing out, someone asked about XPU stats. This is the stat system for XPU. And moving from 24 on, it will be the same system for both XPU and RIS. And we'll also expand instrumentation in the Bridge products. And we'll focus on building more live listener plugins as well. We also plan to package up a lot of the utilities and tools that we're building into a listener SDK for 25.0. In 25.0 also, the legacy stats are slated for retirement. And in the meantime, the RenderMan team is available and willing to help with transitioning pipelines to the new system. So yeah, that's our new stat system. Thanks. It is time for Q&A. If all the other presenters would come back on stage, and I'll hand it back to David Hackett.
Hello, everybody. It's me again. We'll wait for Philippe to hop on for it. So thanks, everybody, for the great presentations. And it's time for Q&A. We'll be going over some of the questions that have happened in the questions tab. So you just saw a lot of the stats work. So those of you who are asking questions in the chat section, don't forget to go over to the questions tab. So one of the first questions we have, and Tom, this one might be good for you down at the studio, is how do you define a technical director? Like what types of tasks and roles do you see most of them in at Pixar?
So Pixar's technical director definition is people who have some artistic and some technical ability. So whereas you could say, oh, that's unfair on software engineers who can paint or draw, but in terms of their work roles, some of our TDs are lighters or shaders or textures or modelers, but then some of them are purely up the tech end, such as myself, without an artistic bone in their body, and I'm optimization and pipeline engineering and that sort of stuff. But it's a wide gamut between those sort of disciplines.
So do you find yourself as a TD kind of helping artists with some of the trouble shots and more difficult tasks?
Yeah, it's one of the cool things about working as a TD is I get to work with people who are incredibly artistically talented to the point where I'm in awe of what they can do, the sort of the intuitions they just make and do, like, oh, I know what to do to make that thing look cool, and they do it and it looks cool, and I can't understand how they knew that. It's a fantastic side of the job, and I'm really happy to be able to help them do that.
Great. And then Per, you had mentioned that this blue noise paper was one of the more recent ones that had come out from last year, but you also mentioned, that we use some of our own research into the multi-jitter samples. Can you explain how maybe the blue noise and the multi-jitter samples kind of build on one another or work together?
Sure. Yes. So in each pixel we use a progressive multi-jitter sample sequence, like we have in several releases of RenderMan. I would describe the blue noise as a thin layer on top of that. So it's basically just a better way of picking which progressively multi-jitter sample sequence you want to have in each pixel. So previously, each pixel, because it's using this progressively multi-jitter sample sequence, it has low error and fast convergence and all of those good things. but it would be completely independent of the neighbor pixel. So they could conspire to kind of use similar sample sequences. There was nothing preventing that. And that's why you see those clusters of dark pixels or clusters of bright pixels. Whereas now those same sample sequences have been optimized in such a way that they're better distributed across the image. So neighbor pixels are better coordinated in that sense. So it's a nice layer on top of the regular sample sequences is how I would describe it.
Great, thank you very much. We also had somebody ask if there's going to be some OSL training on the RenderMan site, and actually I can handle that one for you. We are actually introducing a lot more training materials. So a lot of the things that you've seen even in this presentation, from how to integrate stats into your system to OSL to others, are certainly topics that we're looking forward to add to the website for training to kind of help you build all of this new technology into your pipeline and take control of your renders. And then we actually have a really good stats question. This is a good one. So do you have any idea now how stats are going to handle checkpointing, or do you have any of that in the plans?
That is almost finished. We have that in play. The way that we have it working is that it will be writing information out on each checkpoint and each exit and each attempt of the render, and you'll be able to gather that information, compare checkpoints, or configure how it's written at the end and whether or not you want to preserve all those checkpoints. And we're also talking about ways to view those iterations to be able to compare them. Tom, you sounds like you had something you wanted to add.
Yeah, so one thing that we realized when talking to different clients about their desires for resume and checkpointing and the rest is they had different wants in terms of how they wanted to aggregate the numbers that were coming out of the different attempts at rendering a frame. And so our design makes sure that no information is lost by the stat system. And so all of the info from all of the attempts at getting through a render is available in the one stats file. And that can therefore be presented in summary, but also separately. So that you can, like let's say you got a job kicked off your cloud render, then you can find the stats for just that section of the render, and then you can have a look at the stats of how it was picked up and continued afterwards. And so you can get a good measure of things like what was my overhead where I had to reload the scene. It's obviously the desire. But yes, it's being built in as one of the primary things we can do with the new stat system.
It'll be there with the 24.0 release.
Yeah.
Great, perfect, no waiting, even better. So we actually just got done talking about all the stats and looking at the performance of your renderer. So this question is actually for Philippe, curveball. Some people have asked about if you've seen or noticed any sort of performance changes when moving to OSL for patterns and things of that nature.
So it's something that's quite difficult to measure because sometimes you gain just because OSL is able to get rid of the unused code path that exists in many places. So then you have a win. And sometimes you have some things that are slightly slower. So I would say overall it's about the same. It really depends how you build your shading networks. But the larger the networks in general, and the more likely you are to get better performance.
Okay, and then still for Philippe, somebody is wondering about the difference between using something like ACES versus standard sRGB. Do you notice any sort of performance or any kind of drawbacks in changing from one to the other?
So if you use ACES, everything looks better. And if you, yeah, no, it's true. But if you pre-convert your textures to the correct color space, it means you have zero additional work to do. And the things that happen inside the core renderer, like the fact that the lights are adapting automatically to your OpenColorIO configuration, has been written in such a way that there is zero impact. That's done just once and reused throughout the duration of the render. So use ACES, use ACES, use ACES. If you don't, well, that's just sad for you.
So to be clear, you're saying we should use ACEs?
Kind of.
Okay, fair enough. So Per, someone has a question on some of the blue noise. So introducing this into the sampling system, of course, means it's going to affect everything in the frame. Are there any usage scenarios or cases where it may not provide necessarily better performance? So something like maybe hair or fur or really thin items, would there be times that you wouldn't want it?
I think it will work just fine on fine hair and fur. There is an interesting issue which was brought up by this is a request by ILM, and they brought up the point that they have the denoiser which was trained. The training data was, the old school noise patterns. So before they can go ahead and use RenderMan 24 with the new blue noise samples, they need to retrain their denoiser, basically. So for that purpose, in that in-between period, they asked for an op so that you can turn off the blue noise. So yes, we're providing that. But hopefully there won't be any other reason to turn it off.
All right, that sounds good. Just leave it on and run it. So here's a stats question for Tom or Trina. Someone was wondering if they could be sent to the stats, that is, could be sent to a different machine for later analysis, or if they could possibly be visualized with some other tool.
Yes, and yes. That's the beauty of having an extensible plugin system. By sending the stats to another machine, I'm not sure whether you mean live or after the fact, but either one could happen. Actually, that's part of what Tom was showing, is he was running a render on one machine and rendering and displaying it on another machine. Tom, you can elaborate if you like.
Yeah, so we support 2 protocols for machine-to-machine transfer out of the box. So we've got WebSocket, we've got gRPC. And so you can have clients at the other end, which don't have to be web-based. It could be a thing that is catching the stats that are sent over and then adding them to a database for later analysis. Or, the current approach of saving files out in the working directory of the renderer, that will still be there in some form and work. That we're probably not going to use XML for the purpose. And then it's how you take that file and process it. The point of the plugin system is if you have the capacity, then you can configure it to change how it works to your heart's desire.
So the JSON file, so part of what would be within the 24.0 deliverable is the JSON file output. So that file in and of itself is the replacement of the XML, but that can be taken and configured and pushed into a database or pushed into a web page or however you want to configure it. And we will include some ways of displaying that, but a lot of that is also fun for you guys to develop.
Great. And then Philippe, you might actually be able to help answer this one. Someone was asking why we only support the .text, and if you know the advantages over some of the open formats. I know that you've worked a lot, especially with a lot of the texture work and rewriting everything in OSL. So could you maybe explain why we prefer our own format?
So our own format is and is not our own format because we support the Pixar format, which is our own, but we also support EXR and TIFF. So if you look at the command line arguments of TXMake, you will see that you have those options available, and the performance is pretty much the same across the board. The Pixar format has a slight edge in terms of compression, but OpenEXR now is probably your best bet, especially if you're using ACEs, because you will need to preserve have a larger bit depth to preserve the whole color range and all the subtleties that you have to encode now in textures. But otherwise, one of the main reasons why we render text and not a PNG or a JPEG is just because these are textures, not images, and textures contain MIP mapping and tiling. So it means that we can randomly access any tile at any point really efficiently and make sure that our memory consumption is always under control.
Nice. And just to let everyone know, the OSL implementations that we're going to have in 24 are 1.11 plus, so it's a little more modern than what you're currently seeing out there. just to give you an idea of what to prepare for as it's released. Getting pretty close to time on this. So if anyone has any other questions, of course, we can take just a couple more. Oh, yeah.
I have a small thing to say about ACEs.
Perfect.
Some people think that, you know, it's too complicated, and it's kind of, they think that they have to use ACEs, but ACEs is just a way to make sure that you render in a much wider color space than what you do usually. And once you've done that, you are completely free to then take these really wide gamut images and turn them into the color space of your choice. So if you want to output to Rec 2020 or P3 or, you know, whatever you need, even if it's like a completely custom color space, it's absolutely doable. So there's, you know, you can render in ACES all the time and then output to different formats without any issue.
Let's actually do another one of our stats questions. We're getting pretty close to time here, but we're the last session, so we can squeeze in a couple more. So are you looking at introducing any of the other sorts of timers based on the information available, so you can just scroll through the different timers? So maybe one for rays and one for you know, any other breakdown of anything else you're trying to specifically look at.
Yeah, so I mean, one of the philosophies behind the system is having worked out a system where you can add a whole bunch of things without overhead, where they only add overhead when you actually query them. We want to instrument as much as we possibly can. So we want to put, one of the points in Trina's early slides was, we don't know exactly what someone will care about. And so we want to put as much instrumentation into the renderer and have it be things you can pull on and read. And therefore, yeah, we'll add as many timers as we can think of, and then hopefully, you know, one of them will be the thing that's the thing you want to pull on for your problem.
Sounds good. And of course, you've already mentioned that you're expecting people to be able to or want to customize their views. So is this something they can also customize their own view for?
Yeah, I mean, they can't add their own timers because that would involve them changing our source code, but they can add the timers that we have pre-added as copious as possible that they decide they want to view and how they want to configure the view to see the things that are important to their renders.
And someone asked about adding code to custom DSOs, and that's what part of the instrumentation API is for. You can add your own timers to your code, and that will be passed through our stat system and end up with all the other stats.
Perfect. That sounds great. Really nicely extensible, and you can add your own things. A lot of larger pipelines kind of do that. And is this going to be something that's going to be available in all of our RenderMans? It's going to be in XPU, non-commercial, and commercial, all built in?
All the above.
Yeah, in fact, I think it'll be the only stat system in XPU.
Yep, and it'll be all bridge products as well.
Great. Everybody will have access to it.
Mm-hmm.
So I'd like to thank everybody for joining us today. We've got our 45-minute session is just a smidgen over, and some of you may have places to go. We'd like to thank everybody for coming to all of the RenderMan Art and Science Fair. This has actually been really great for us to see everybody, and we're happy to see everybody. You have no idea how nice it is to actually see all of this when we're, you know, kind of holed up in the office all day. It's nice to actually see all these faces and all the questions. And also, don't forget about our Teapot AR challenge that's already live. Make sure you download your little AR Teapot and get some images up on Instagram and be out there and compete and take a great look at it. And again, thanks for tuning in. These will be available online shortly after they're all completed and will be up for a little while. So if you missed something, feel free to come back and watch again and again. So thanks again.
And again.
All our presenters.
Bye-bye.
Thanks.